welcome. In this recording, I'm gonna to describe a kind of algorithm to solve some problems, which combines two stages. The first stage is about the construction, where we apply a greedy algorithm. This algorithm applies an heuristic function in order to select each of these solution components that are going to be inserted here. For instance, at the beginning, this heuristic function might decide to include here the solution component B. Afterwards, it might decide to include the solutions component C, E, and so on. And perhaps at the end, at the end of that stage, you got the solution, and you, in this new stage, you apply local search, where the current solution undergoes some modifications according to the neighborhood operator. So, for instance, let's suppose that the elements between these two are written in the opposite direction. So the new solution is, in this case, is this one. And if this is the solution which is accepted, this neighbor becomes the current solution, and this process applies until there is not any neighbor which is better than the current solution. This algorithm is a mixture of greedy construction and local search. The goal is that this description will be useful to understand other algorithms which are grasp methods. So how this gradient local search applies? Well, I will use this problem instance where we would like to find a good circuit that visits each of these cities, each of these points, and there is a possible arc, a possible edge between any pair of these points. From previous slides, you might know that the optimal solution is this one, which is encoded this way. So in this case, we have started in the optimal solution. We have started from city A. Afterwards, we have traveled to city B. Afterwards, to city C, and so on. And the cost of this circuit is 226.64. So how do we apply the greedy construction? The first stage of the method I'm describing. Let's suppose that we draw randomly the initial city, the initial point. So a good heuristic for this problem, the TSP, is to travel to the closest city. So which is the closest city from A? The closest is B. So we will travel to B. Afterwards, C, F, G. Here you can observe that the closest city from G is J, so we will travel to J. Afterwards, K, H, E, D, H, E, D. Afterward, the closest city from D, which has not been still visited, is M. So we will travel to M. The next one is, let me check it. The next one is N. P O L I Q, we return back to A. So P O L I Q A. This is the the circuit produced by the Grady constructor. So at this point we have finished the Grady construction, and we will move to the second stage, which is the local search improvement. Let's suppose that here we test different two OPT operators which just select two positions and invert the substring in the middle, and the one we select is this one. So in this case we have inverted the substring, and we have produced this new solution. Well, the first time is a bit difficult, but once you can notice that this new solution just removes the edges from G to J, so this edge is removed, and the edge from D to M. So this one is removed. And the new edges are G to D, which is this one, and J to M, which is this one. So, well, here you can observe that this is an improvement because the sum of the cost of the red arcs is less than the sum of the cost of the arcs we have removed. So after this operation we obtain this new solution, which is better, and we could still try to improve this solution with other OPT operations. So for instance, in this case we could invert these last elements. So the new solution would be A, B, C, F, G, D, E, H, K, J, M, N, Q, I, L, O, P. And in this situation, in this occasion, the arcs we have removed are those between N and P and Q and A. So this one, and this one. And the arcs that have been introduced are those between N and Q, so this one, and P and A. And here, as before, you can observe that the sum of the cost of these new arcs is less than the sum of the cost of the previous arcs. So after this operation, the new solution is this one. And we could still apply local search, in fact, until there is no any improvement. In this case, well, I have not made the computations, but in this case, with not too many points, it is probable somehow to a certain level that we might obtain the optimal solution. But you should think of a very larger problem. If the problem had a kind of 100 cities, so you know that there is 100 factorial different, well, not actually circuit, but different permutations of the cities. So there are so many possible solutions for this problem that it is very unlikely that we obtain the optimal solution with this procedure, greedy and local search. And here comes the drawback of this procedure. If it is improbable or unlikely to obtain the optimal solution, the problem is that the greedy constructor takes a lot of deterministic decisions. So at the beginning it produces this solution, which is, well, not too bad, not too good. This solution can be improved with the local search, and the local search might end up in this local optimum. If we apply again the same procedure, the greedy constructor probably produces the same solution. And the local search, if the local search also makes a lot of deterministic decisions, it will repeat the process and will end up in the same local optimum. We can repeat this process a lot of time, and if there are not random decisions, or they are very infrequent, they are not very frequently applied, then the initial solution probably will be the same always, and the local search will be the same always. We will have no opportunity to reach better solutions here. So that's why the subsequent method appears, grasp, which is going to be described in another video.